Hello everyone and welcome to this section. In this section, we're going to discover one of the famous kind of training strategies or training techniques, which we'll call it backpropagation, all right? Again, we're not gonna dig into the math. There's a lot of math behind it. Here, I'm just gonna give you the intuition because what we're gonna do is I'm gonna use the actual training strategy to train our network moving forward in the Python and Jupyter notebook. All right, so just a quick overview of the training strategy. So what we do, what we have is first we have our input data and we have our target class or our true data, okay, true label data. What we do again, as I showed you earlier, we show the network this input and the correct output, and the network calculate the error signal, okay, between the predictions and our true class. We use the error signal, simply we go back and update the weights. That's pretty much the training, how we perform training in general. All right. So training in backpropagation strategy actually works kind of in a four steps. First step is what we call it the forward propagation. That's actually what we have done before in an actual practical example. If you guys recall that we have an actual true numbers. We actually ran through the network. Okay. We have inputs. We multiply the inputs by the weights. We apply the activation functions, and then the output we're gonna, like if we have a multi-layer perceptron network, actually the output we're gonna be using as input for the next hidden layer. And then whatever output we're gonna be generated, we're gonna be used again for the next hidden layer, and then we keep forward, and then we actually generate the actual output from the whole overall network, okay? That's the first step. So the input starts to propagate, which is step one, what we call it forward propagation, through the first layer, input layer, and then going to the hidden layer, going forward to the output layer, and then we generate an output, all right? That's the first step. Next step is that we do what we call error calculation. That's step two. We actually have our true class, okay? We subtract the predictions minus what we know, minus the true value. And actually what we hope or what we love is that the network will generate error of 0, which means our predictions were perfect, okay, from the beginning. But obviously that doesn't happen. You can't have a baby or a kid that knows everything from scratch from the beginning, it has nothing to learn. That doesn't work. Okay, in general, like the kid, for example, will mess up in the beginning, and then through learning, through measuring, through like falling down and stepping up and doing these like series of errors, can we calculate the error and actually go back and teach it or teach him or her on learning and make him learn how to walk, for example, in the same fashion that as we do it here. We calculate an error signal, and then that's the key element. We go back to the network, so we call it the backpropagation, okay? And we do what we call it weight update. We just go back and update the weights here in a very, very simple form, okay? Weights in the beginning are random, okay? That's why the output would be like kind of garbage in the beginning. As we learn, as we move forward, we go back, these weights starts to get updated, we get better, we get, the error goes down until we actually stop, and then we have our network with, with a great number of weights, and we're good to go, all right? So backpropagation is a method can be used to train artificial neural networks by calculating what we call it gradient values that can be used to update our weights, okay? It's commonly used mainly, and what we use is mainly what we call a gradient descent optimization algorithm that can be used to just optimize our network weights, all right? Okay, let's dig a little bit deeper into the backpropagation and get an idea of what's happening, all right? Okay, so the first step or the first phase, again, is what we call it, we summarize step 1, 2, and 3, we call it like phase 1. Propagation through the network, we calculate the cost, or we call it the error term, and then what we do is that we propagate the output back through the network, through the backpropagation, okay? What we do is that we calculate what we call it the deltas, or the difference between the target and actual values, all right? Okay, and then the phase 2, which is what we do in general, is we do weight update, okay? So once we calculate the gradient, okay, we go back and update the weights. The key element here is, okay, how much do I need to update the weights? Okay, you can go very aggressive and use, for example, the error value or these gradient values and actually multiply it, let's say, by 4, which means you are increasing what we call the learning rate, okay? All right, and that's actually one of the tunable parameters that we could use moving forward in the training, is what we call it learning rate. What percentage are we gonna use out of that weights gradient to actually go back and update the weights? If you wanna go really aggressive, learn really fast, we're gonna use very high learning rate, okay, in there, all right? However, if you use like kind of, so again, the greater the ratio, greater the learning rate, the faster the neurons train. However, if we use a lower value, then the more accurate the training going to be is. Yeah, it might take longer time, but we're going to achieve kind of, like more accurate results. all right? And that's again kind of backpropagation in a nutshell. If you guys want to need like a dig into like the math behind it, you guys can read these kind of 2 papers, Backpropagation Neural Networks, kind of a tutorial, and Improved Backpropagation Learning in Neural Networks using windowed momentum, all right? Again, there's tons of papers. If you guys can just go and look backpropagations, a lot of papers out there. We're gonna discuss the math behind it. Here, literally, we're just gonna use it in Python. We're just gonna use just one command that does everything for us, okay? And again, now we know the intuition, because intuition is important as well to understand what's happening, to understand what we're actually working on, what we are updating, which is in this case, we're just updating the weights and the biases, all right? Okay. So the question is, how can we assess our training technique? Actually, we covered that before. Here, I'm just gonna touch base on it a little bit quicker. So first step is what we call the speed of conversions, which is how many epochs we're gonna be using, the first step. The faster to minimize the output error, the better. So hopefully we can achieve, our best accuracy in like 2 or 3 epochs. That's great, okay? Especially if you're using kind of, what we call online training algorithm. We're actually training the network as we go, okay? Here, we're just gonna use an offline training. We're just gonna simply train the network. Once we have a trained network, we're just gonna put it in practice, okay? Use testing data to actually test our network. The next step is what we call a generalization capability. We would love to have our network generalize as much as possible. Again, if the network can see all images of cars on the internet, it can actually tell us, okay, these are actual cars, okay? It can generalize, all right? And then the next step is, which is important as well in network training, is what we call it, the key to avoid premature conversions to local minima problem. What we hate, again, is for network to be stuck in what we call local minima problem. What we love or what we need is to achieve what we call the global minima problem, which is the largest, the most minimum value within the entire weight space. So we have various combination of weights. We want the best combination that can tell us exactly this point, which is the minimum or the global minimum within our error. All right, and that's pretty much all what I have for this section. I hope you guys enjoyed it, and see you in the next section.